Okay, thank you everyone for coming today to this meetup. This is Julia User Group Munich. I'm Stefan Sam, as usual. Every second month, getting a speaker in. Today from Beijing. Thank you very much, June, for joining us today. I'm looking forward to our session on reinforcement learning. You are invited to ask questions, so you can raise your voice, click this little raise hand button, or just type things into the chat. I myself will also have an eye on the chat, and there are also others who can help in the chat and answer questions right away or raise it then. So so that June can answer all your questions. Okay, so thank you, June, for being here. Just a short intro. So June is the main developer of the ReinforcementLearning.jl, which you're going to learn about today. And and he's also part of the Julia CN organization community, and lately joined a startup. So very much into work business, but finding time for pushing this Julia front end. Okay, thank you very much, June, for being here today. Stage is yours.
Okay, thanks to Steven's introduction, and I'm very honored to have this chance to give such a topic. Today I will give a short introduction to practical introduction to ReinforcementLearning.jl. Okay, let's go. So in this talk, the goal is to first we need to understand the past, the current, and the future of RL.jl. And second, I will guide you to master how to apply RL.jl to some interesting problems you might be. And the third is learn how to define a problem we want to solve with RL.jl. So about me, and I acquired the master's degree on natural language understanding at the University of Chinese Academy of Science in 2016. And I get started to use Julia at version 0.6, I think, around 2017. And I'm also an active member in the Julia Singing community in China. My last job at Microsoft was mainly about natural language understanding in dialogue systems, and recently I joined a startup focusing on NLP and RL in games. So as you can see that I'm not a serious reinforcement learning researcher, so correct me if I'm wrong here. Also, feel free to interrupt me if I do not make myself clear. I think reinforcement.jl was started around 2018, and it has been about 4 years since its first day. And actually, it was named tabular reinforcement learning at first, and it was written by Johanny Brie. And one day, Johanny Brie sent me an invitation to work on it together. And after that, I implemented several tabular reinforcement related algorithms from the famous book, the Reinforcement Learning, an Introduction, and the second edition. And after that, we added many deep reinforcement learning related algorithms like DQN or many policy gradient related variants. And also we have added counterfactual regret related variants. And lastly, we have also one student working on offline reinforcement learning. So actually, this package is a result of many different contributors. And some highlights is that the DQN implementation is relatively fast when you compare to with some other packages written in Python. And also the PPO, especially the PPO implementation, is pretty fast. At least based on my benchmark last year. However, I think it's far from perfect. Some people may say that the documentation is still poor, and it's not very easy for newbies to learn this package. And until for now, we do not have a good support for async or distributed RL. And we also have only limited support to multi-action spaces, especially continuous action space. But most of them will be addressed in the next release this summer. So just hold on. Now get back to our topic today, a practical introduction. So the standard setting for reinforcement learning contains two parts, the agent and the environment. And so we can, if we would like to express the whole pipeline in the Julia code, we can use the pipeline operator so that the environment passes to the policy, and the policy will observe the necessary information from the environment. Then it will generate an action and pass the action to the environment. So this is the whole loop. More specifically, we will acquire the current state and the current reward from the environment. This is the two most common information we would need to know for the agent. And the agent then generates an action and put the action back to the environment. And then in the next step, we got the state and the reward again. And then we use it to update the agent so that the loop can run infinitely or any longer if you wish. Now let's see a more concrete example. This example is added in the docs from the official Julia or reinforcement learning org. The environment is a very simple one. Suppose that we have a boat Eva at a position 4 on the axis, and it can either move left or move right, one step at each step. Then if it reaches the position 7, then it gets a reward of +1. And if it reaches the position 1, then it gets a reward of -1. So this is the environment we like to play with. In this environment is already included in reinforcement.jl, so you can, after using reinforcement learning, you can initialize the environment like this. And we can get a state from the environment. Here we get a state from the environment, so the state is 4. Actually, this is just the position, the first position, initial position of the boat. And we can also get a reward from the environment, although we haven't executed any action yet. So the reward is meaningless at the initial state, but still we can get a reward. Also, we have some action space, so you can either turn left or turn right. We encode the left and right information into a vector, of 2 elements, 1 and 2. So when we execute the turn right information, turn right action to the environment, then the environment will, the boat will move 1 step to the right side. And now we get a state again. So we know that the environment is at the position 5. That's pretty much the most of the APIs in reinforcement.jl around the environments. And the second part is policy. So actually, policy could be arbitrarily callable object which takes in an environment and returns action based on the whole definition in the previous slides. But in practice, especially in R.jl, we usually use define a new policy which inherits the abstract policy. I think the simplest one policy is the random policy. So the random policy takes in an action space, and as you can see, the action space is a 2-element vector. And if we feed the environment into the policy, we can see that the policy will generate either action 1 or action 2, which means turn left or turn right randomly. Here I sampled 10 examples. So now we have both policies and environments. The first question we would like to answer is how to simulate the interactions between policies and environments. Well, we have overloaded the run function, and by executing run policy with the environment, we can simulate one episode. But from result in this simple function, it seems nothing happened. But actually, it has already executed for a whole episode. So you get a state, you get a reward, and the check is whether the environment is still terminated. Then you can see that the state is at position 1, which means the boat already reaches the leftmost position, and it has get a reward of -1. And also at this time, the environment is already terminated. And this environment is overridden in, as you can see, is overridden in reinforcement core. And so the second question is, what if we want to stop after several episodes? Well, we can add another argument to the run function. So we tell the run function that we would like to stop the experiment after 10 episodes. In the previous example, we only have stopped the policy and the environment after only 1 episode. Now here we would like to stop, keep running, and stop after episode 10. But what if we want to stop until arbitrary condition meets? Well, in that case, you need to implement your customized stop condition. However, in reinforcement.jl, several common ones are already provided, like stop after step, or stop after episodes, or stop after n seconds, and etc. How to implement these customized stop conditions is out of scope today, but in short, you only need to implement condition given the agent and environment to return true if you really want to stop the run function.
Jun,
Okay.
one question from my side.
Okay,
can
sure.
you go back 2 times? So where you call it with your condition, where you call the run function. Yeah. Here, this environment. And is it initialized again to be an empty, or could we reuse the environment from the slide before?
Actually, it will, every time you execute the run function, it will get resetted. So the environment will automatically reset it.
Ah, okay. So it knows its start position.
Yeah, that is currently hard coded so that the environment will always be resetted internally.
Thanks. Yeah, answers the question. Perfect.
Okay, so I will go ahead. And the third question is how to collect experiment results. Obviously, in here we know that so how to collect experiment results? Usually in an experiment, we would like to know many extra informations, like how many steps we have executed in each episode, or what's the total reward of each episode. Because in the previous example, our reward is very simple. You only get reward at the end of the episode, either 1 or -1. But in other positions, you only get 0 reward. However, in some other environments, we may have reward at each step. So we would like to know the total reward of each episode. And also some other questions like how much has our policy improved in the whole experiment? Or you may find many other such questions you would like to answer in such an experiment. So to answer these questions, many hooks are introduced in RLWL. For example, here we provide a hook named the total reward per episode. And to answer these questions, usually we need to write many customized hooks. And in RLWL, we have already provided several built-in hooks, for example, the total reward per episode, and also some other hooks. For example, this hook will answer the question the total reward per episode. For example, here at episode 1, we get a reward of 1, and we at episode 10 we get a reward of -1. So now we have already learned the 4 core concepts in RWGL: the policy, the environment, the stop condition, and the hook. I think all the things that the RWGL provided are around these 4 concepts. It provides learning built-in different policies, environments, and stop condition and hook. And also people can also write their customized ones. So do you have any question until now? Okay, if not, I will go ahead and to the second part. Now let's take a closer look into policies and environments. So this is a layered picture of very different components of environments and the policies. I will go back to this picture soon. So first, let's see what's happening when we execute the run policy, environment, and stop condition and hook. So actually, when we execute this run function, the policy is running in the active mode, or someone would call it in the test mode, because here the policy won't try to optimize itself. It simply take the state from environment and get the environment and pass the state of the environment to the policy. Then the policy return action. The policy usually is a pure one. It won't optimize it. So in the above picture, the state follow the yellow arrow, and then it will pass directly to the policy. And the policy generates an action and pass back to the environment. So it follows this path. And we can see some examples instead. In the previous example, we are using a random policy, but here we will use a more complicated policy named queue-based policy. So a queue-based policy has only 2 paths, a learner and an explorer. The learner can be many different components. Its main goal is to predict the queue value, and the explorer will try to decide which action to return given the queue values estimated from the learner. So as you can see here, we are using a Monte Carlo learner. And when we feed the environment to the policy, we will generate an action. Here it simply returns action 2, which means turning right. And we run the policy and the environment on also the stop condition hook again. You can see that it always it will always get a reward of -1 here. So we would like to ask, obviously, this is not what we want, because we would like to, usually people would like to assume that the learner could improve slightly when we train enough time. But actually, here the reason is that when we get the state from the environment, our learner always predict the state and return a queue value of both 0 and 0. This means that at each state of the environment, the value to turn left and turn right are all zeros, because our learner is initialized with all 0, and so here we do not have any preference over these 2 options or these 2 actions. And remember that we have already defined an epsilon grid explorer, which will select the turn left action, the first one of the maximum queue value first. So we will always, or in most cases, with the probability of 0.95 to turn left. And that's why we, in the above figure, we get a reward of -1 here. So obviously that is not what we want. And we would like the policy to improve if we run the loop for several episodes. So in the design of RL.jl, we use a wrapper to run the environment and policy in the training mode. We provide a special policy wrapper which is named the agent. The agent will cover the policy and together with the trajectory. So the agent has two parts, a policy and the trajectory. The policy, as you can see, is the previous policy we have defined, and now we have the agent. Now let's come back to the picture again. Here, the policy could be a random policy or a queue-based policy, which would like to learn the queue values. And now the workflow is slightly changed. When we wrap the policy in an agent, we first get a state from the inf, and now the state and the reward flows first to the memory buffer. Then it will also pass to the policy and the general action back to the environment. But at some proper time, the agent will decide that now it's time to optimize our policy. Okay, then it will automatically sample an experiment batch from the memory buffer, or people would call it experiment replay buffer, and then send the batch to the policy, and call the policy to optimize it itself. And usually in DQN or deep RL, we would like to optimize the neural network in the nutshell. So that's pretty much the whole story of the training mode. And I think this is the most confusing concept for people to use RL.jl for the first time. Once you have understand the differences, I think things will be much straightforward when you apply those algorithms. As you can see now, when we run the agent and environment again, we can see the total reward improved from -1 to 1. One thing I didn't cover in the tutorial of the docs is that you may find one interesting problem. So let's take a closer look into the totalness of each episode. Okay, as you can see that in most cases, we only need to take 3 steps to turn the boat from position 4 to position 7. However, as you can see here that at the episode turn, it takes about 5 steps to reach the position of 7. So it may be confusing to people because we have already trained our policy to a very good state, but why would it still occasionally behave unexpected? The problem lies in that here in the inside of our agent, the policy, especially in the policy, let's say that our explorer is still an epsilon greedy explorer. So with such an epsilon greedy explorer, it still has some chance here. The chance is 0.1 to choose a random action. So if you would like to avoid such case, you need to create a new policy. Here I will create a fresh new policy which is still a queue-based policy, but the learner is the previous learner. However, we use a different explorer named Greedy Explorer here. So as you can see that in this case, our new policy always select the greedy action, and the length of each episode is always 3. Okay, so any question till now? I hope that I didn't make it too fast.
I would have a question again. Thanks, June. So the learning now happened just because we wrapped our policy in an agent, but then the run function was actually also executing the learning part. Or so this here, the run function was triggering learning as well.
Yeah, that's a good question. So when we wrap a policy in an agent, now we have another dispatch of the run function. So it is not the same as the original one. In the original one, we will just execute the policy and get reaction. But if you wrap it in an agent, the agent will do something before here, as you can see that before it sent to before it send the state to the inner policy, it will do something like insert the state to the memory buffer first. So actually we have leveraged the multiple dispatch in Julia so that we overwritten the original one. Yeah, that's pretty much the whole story behind that.
Thank you. And the agent is then learning still step by step, or so episode by episode. It has one run,
well,
and then
that's
optimize
so,
it.
Yeah, that usually people, I think different policy has different strategies. So in RWGL, this part is still customizable since the agent we recognize that in most cases, people would update the policy every several steps. But in some other cases, people would like to update the policy at the end of the episode, or like you said, several episodes. In that case, you need to implement your specialized methods so that you can control when to optimize the policy. And in RWGL, it has only implemented a very common one. Yeah.
Thank you.
But in your example, was the agent requesting a learning step at each episode? It's just not clear. I'm.
Okay, so here in this example, since it is using the queue-based, it is using the Monte Carlo learner, so it will only update the learner at the end of the episode. So here we are using the Monte Carlo learner. So for Monte Carlo related methods, you can only update the Q value only after the end of the episode. Yeah.
Okay, so so the learning is happening after every episode is completed.
Yeah, exactly.
Okay.
I've got another question which might be a bit artificial, but like imagine I would like to implement a Monte Carlo exploring starts algorithm. You said in the environment, the starting state is hard-coded, but for that I would actually need to vary the starting state in there. Could I do that just with your setup, or would I have to manipulate the environment in some way?
I think the best strategy is to write a customized policy named like Monte Carlo. Sorry, what policy would you like to say? So
not a specific policy maybe, but like exploring starts, so not starting from this fixed point at 4, but like at any possible position.
Yeah, so in that case, I would suggest to write a customized policy wrapper to wrap the inner policy. For example, if you write a exploring start policy at the first several steps, and then you wrap the policy. You wrap the policy. For example, the Q-based policy. You wrap the Q-based policy and this random start policy, and then wrap it under the agent, so that you can pass the state to the policy of the random policy, so that the action is still generated by the exploring start policy. I hope.
Yeah. Thanks a lot. That made things a lot clearer.
Yeah. Okay. Okay, now I will go ahead. And to apply R.GL in real-world problems, usually we would have two common questions. Like the first one is how to choose the proper algorithm, and the second one is how to describe the problem in a recognizable way. Well, before answering these two questions, I would like to give a short introduction to the trajectories structure first. So since the trajectory-related code is still will end a big change in the next release, I will use some coding development to explain things clearly to you. Although I think the name is slightly different from the current implementation of the code in R.GL, but the idea share the same. So first, we can create the agent. When initializing an agent, we create a policy and a trajectory. The trajectory here, for example, I initialize a secondary state action reward terminal traces with a capacity of 10. And at the initial state, it is all each trace in the traces or trajectory is empty. And the size is defined. You can customize the size of the state and action with actual keyword parameters. And then we push at the beginning of each episode, we push the state and our action generated from the agent into the trajectory. For example, here at the start of the game, we are at the state 4 and we decide to turn left, and our action is 1. So we push the state and action into the trace at the beginning of the episode. After that, for example, here, after executing the turn left action, we get a reward of 0, and the terminal info is false, signaling that the game is not terminated yet, and we reach a new state of state 3. And this time, our inner policy tells us that keep executing turning left action, so the action is 1. And the agent will put this information into the traces. So now we have state 4, 1, reward 0, and the terminal false, and also the next state of 3 and 1. So notice that we store state action and the next state and action in a compact way. If we do not consider the memory consumption, we can allocate another 2 traces named next state and next action, and we flatten the state action. But usually, we would like to keep the memory consumption as low as much. So we reuse the state and action traces here. Always remember that when one step finishes, the length of the state action is 1 step longer than the reward and terminal. And then we keep collecting new experience and pushing them into the traces. And also, until we reach the end of episode, the terminal signal is true. Now here we get as you can see, the terminal info, the last element in the terminal info is true, and we get a reward of -1, and the state and the action. And the final state and action is 1 and 1. Also, although the last action actually is meaningless, but we mean to keep the length of the action same to the length of the state. So we inserted this meaningless action into the traces. Note that all these behaviors are handled by the agent, so you don't need to care too much about when to insert such state and action or reward terminal info into the trajectory. And we already have very good default methods implemented. However, in some cases, you still need to customize the information, and I believe actually it will quite painful to customize such things if we do not have standard code in previous version. And I'm working on improving this part. And in the new version of the trajectories, it will be very easy or more straightforward to implement some customized logic with how to update the traces, and how to sample a batch of experience from it. Now let's come back to the algorithm part. Usually, two most commonly used algorithms are DQN or A-Lines and the PPO, I think. And especially thanks to Henry Dehe, he just wrote a blog, updated a doc on how to implement new algorithms. So I won't cover it here today. And in the rest of the part, I will mainly introduce how to use these two commonly used algorithms. Okay, here I'm using the famous Catpole environment to demonstrate. Here, the policy, let's say, so here we use still we are using the queue-based policy, but the policy is slightly different from the previous one. It is using the basic DQ learner. In the previous example, we are using the Monte Carlo learner, but here we are using a basic DQ learner, so that we are trying to apply the DQ algorithm which uses a neural network to approximate the Q values. Here the batch size and also the minimal replay history are used to tell the agent how to sample an experience batch from the trajectory to update the internal approximator. Here we are using a neural network approximator, and the model can be defined using flux structure. For example, here the dance or the chain are all from the flux.gl package. And also the optimizer used to update the model. And this is the whole structure you need to define a DQN policy. I think the policy part and the trajectory part you are already familiar with. One thing you need to note is that queue-based policy usually runs only with the circular array SCRT trajectory. And in many cases, if you use a policy and if you do not use the matching trajectory, and usually it will trigger an error. Although I have predefined some checking points in the running function, but I think it is not triggered yet. So you still need to be careful that when you are using queue-based policy, you need to define the trajectory correctly. And here, since our state is just I think this should be a float here instead of a vector. Any case, anyway, I will check it later. And another important one is to make sure that the state of a trajectory matches the environment. You get the state from the environment. So now we have defined our policy. And then, as usual, we define the stop condition and hook. Then we run the policy environment with the stop condition and stop condition and the hook. And now we can see the result. Well, for the PPO policy, it is kind of different because for PPO, the environment, usually we can simulate several replicas together. So the environment is kind of different from what we have defined before. Here we use a multi-thread environment to define several replicas. Here I defined 8 replicas so that this environment is actually a wrapper of 8 independent internal cut pole environments. And we reset the environment at the initial step. And now to define a PPO policy, still we need to wrap it in an agent. And now, note that in PPO policy, we do not have a learner anymore because the learner is only, in most cases, the learner is only specific to Q-based policies or V-value-based policies because the learner is used to estimate the Q values. But in PPO-related policy, we will get an action directly based on our policy. So here we only need to define the approximator. And it is an actor critic pulse approximator here. Also note that the trajectory we use here is slightly different from before because we have defined a special field named action or probability. This is just a special variant for the PPO implementation. I think in some other cases we can also reuse the secondary state action reward terminal trajectory, but it is not implemented in R.gl yet. And similar like what we did before, we ran out the experiment. We define an agent, environment, and the stop condition and hook. One thing I did mention is that when you apply a new policy to the environment you would like to solve, usually it will take a lot of time to tune the parameters. Really, I think this is kind of tricky. I understand that actually it's very tricky to select the best parameter to tune the, especially when you want to solve a fresh new environment. It's kind of very difficult and time cost. And maybe in the future we will try to do some parameter searching strategies and add it in this package. Actually, I think the first policy I would recommend people to try is PPO, not only because it is fast, but it also have a wide the support for many different kind of environments, especially thanks to Alvin's help. That now the PPO supports multiple continuous action space. Actually, the PPO policy is one of the most commonly used and also mostly studied algorithm. And for example, here in this link, this is a blog posted several months ago. and it documented 37 implementation details of the PPO. Since RL.gr is very flexible, most of them are pretty easy or straightforward to implement with RL.gr, but currently the built-in one is only one variant implementation, and I think it is not the best one. So I encourage people, if you would like to use PPO, you can check out that blog and then come back to the source code of the PPO implementing RL.gr and compare the differences. Okay, so the next part is about environments. For most simple environments, the interfaces defined in common R interface would be enough. You only need to implement such several methods so that the environment you defined in common R interface will be recognizable in R.gr. The benefit is that you can also try some other packages like POM-DP and also like alpha0.gl. You can use those packages to try some other algorithm instead of those implementing R.gl. Or if you prefer the interface defining R base, you can find many examples in the R environments, the subfolder and the R.gl package. And I think I have most of many different kind of environments also covered in the examples folder. Here, I will simply go through the simplest one, the multi-unbounded environments. And in this environment, we need first to
sorry, June, just before you go on, one further remark. I just checked the names you mentioned, RL base and RLN. So maybe you just mentioned it, but it was confusing me a little bit. So I just looked it up. So they are really sub packages of the RL package. Huh? So it's really just reinforcement learning.rl base, and you get these. They are not different packages, but yeah, part of the package we're speaking about.
Sorry, I forgot to mention is that I think the best is to, I think the best one is we can go through the homepage of reinforcement.gl and yeah, we can check since for most users, we can simply use reinforcement.gl and all the exported functions or variables defined in those sub-packages are exported in R.gl. So in most cases, you only need to use R.gl. And several other packages, sub-packages existed to help organize the code structure. For example, our base, our environments, our core, our zoo, and also this is still in the development of distributed R.gl. So what I mentioned in the previous slide is reinforcement environments. And I have already covered a lot of examples here. So these examples are very simple ones so that it will help you understand. You will first try to think which environment is close to the problem you want to solve, and then look up the source code and learn how to implement them. And I think I have tried my best to add docstring to those methods. So yeah, I hope I have answered your question clearly.
Yeah, thank you very much. There's actually a hand raised from Philippos. Please.
Oh. Okay.
Yeah, hello.
Okay.
Actually, I had the question regarding this very structure of the project.
Okay.
So I was wondering, it was one of the confusion points I had when I first came across this package. And I guess the question is, why are they implemented as sub packages and not as diverse packages in the Julia registry? there any reason behind it?
Yeah, good question. So, as I said before, only developers need to care about those sub packages, and the reason behind such organization is that the reinforcement base package is actually very close to the to common IR interface. We would like to define a set of common interface so that for example, if people defined some other environments, or for example, people write a wrapper of another environment, then if he only needs to implement the interface defining RR base so that he only needs to import RR base only instead of the whole reinforcement.jl package. Because the whole reinforcement package is quite huge. It has many large dependencies like flux.jl, qdar.jl, and people registering independent third-party environments do not need to rely on the whole RR.jl, but instead, he or she only needs to rely on RR-base.jl. And for example, lastly, we have a GSOC student working on the gridwords.jl, this environment. So, for example, here, he has implemented, Siddharth has implemented many interesting environments in the gridwords.jl, but he do not need to add the dependency of the whole reinforcement.jl. He only needs to add the dependency to RBase.jl. That's the main reason. And as for reinforcement core and zoo, because the reinforcement zoo contains several built-in implementations like DQN or policy gradient related algorithms. But if people, for example, people published another algorithm, they do not need to contribute back into the R.jl directly, since maintaining such an algorithm, maybe because maintaining such a package is not the interest of the author, so he can register that package independently, and he only needs to add the dependency to reinforcement in core.jl. Yeah, I think that's the main design decision and the such structure of those sub packages.
Yeah, I see. And right now all these packages are implemented as modules in the reinforcement learning package, but then they are being re-exported as packages also. Because these are also subfolders inside the source folder, and each one of them defines a module.
Philippus, I think the confusion came from my side. Ah, no, they are indeed defined as subfolders. Yeah. Okay.
So the question is, are they needed to be as the source there as sub-modules, or they can be
actually I understand. There's no sub-modules. They are independent packages. It's only that they are organized under the same source folder. So as you can see, and here, we do not include those sub-packages. So these are independent modules or independent packages. Yeah.
Okay, so I guess the way to think of it is that every one of them is really an independent package, and it's just that the reinforcement rl.jl unites them together.
Yeah. I'm not sure I understand it clearly.
Yes, I think I understood it the same way, Philippus.
Okay.
Okay, thank you very much.
Okay, thanks. Okay, I will continue.
There's another question actually, if we have more time. Simon also want to ask a question.
Okay. Yes, Thank you. So my question is, you covered it briefly, but could you please elaborate on the differences between reinforcement learning JL and AlphaZero JL? Are there any major common areas? Are there any major common differences between these two packages? How do they relate to each other?
That's a really good question for the end. Just, June, if you want to go on, I mean, it's also fine, but you can answer right away. But it sounds like it's perfect at the very end of your presentation.
Okay. Okay. I think I have only several slides left, so I can answer this at the end of said. Okay.
Okay. Thank you.
Okay. I will go ahead and yeah, that's a pretty good question. I think I have only 3 or 2 slides left. So back to the when we have defined the environment, several things we need to consider if you want to write a new environment in a recommended way. The first one is the state space of the environment. For example, you need to consider the size of the state space. Is there any different representation of the state? For example, the one hot or multi-hot, or you would like to train a consequent state like what we did in the AlphaGo, or split into several different layers. And to decide the action space on environment, you need to have to decide whether the action space to be discrete or continuous. Do you really need a continuous action space? Sometimes you can just use binning. And you also need to decide how large the action space is. Can you reduce the action space further? And also, can you leverage legal action masks? And the third question is, can we effectively run multiple replicas together? All these questions will affect the algorithm you would like to choose to solve such problems. So think of these questions before you really choose one algorithm to apply it to the environment. And based on my experience, the more clear you define the state space and action space, the more easier to solve this problem, and you will choose the best algorithm to solve this problem. Okay, then my last slide is what to expect in the next release, since I have mentioned that several big changes will come in this summer. So the following 3 points are on top of my mind. The first one is a fresh new implementation of async trajectories. This is mainly inspired by the package named DeepMind Acme, one of the dependency of the DeepMind Acme, so that we can train many policies across different nodes or different machines. The second one is to add more experiments on environments where multi-action continuous, especially continuous action spaces, for example, Mujuko. And the third one is an end-to-end GPU training. In that case, the environments will be running on GPU, and the policy will also be running on GPU. The whole pipeline needs a lot of change here. And personally, I will work on some porting the Isaac Gym environment to Junior and to experiment with this pipeline. And to be honest, the IDOJ is hard to compete with many other mature packages written in Python. And part of the reason I think is that we lack active contributors and also active users. But this kind of chicken and egg problem. I think when we have more contributors or when we have more users, the development speed will be much much quicker than before. And yeah, that's some personal thoughts. Okay, so that's almost all the content I would like to share today. And first, I would like to thank you all. And let's come back to the question just raised. The comparison between R.gl and also something like some other packaging like POMDP or alpha0.gl. I think alpha0.gl it is pretty good for many interesting problems. For example, pure some environments with you would like to, because I think this is the relation between R.gl and alpha0 is complementable to each other. So I have explained in the first slide that since R.gl is born with tabular reinforcement.gl, and it mostly focused on some from the introduction level to the practice level like deep RL, but it has never implemented some algorithm like Monte Carlo based algorithm. But AlphaZero did quite well at this part, and also it is very efficient to solve many problems like Go or some other pure information environments. Yeah, that's my personal opinions on how to best use alpha0.gl and R.gl.
Thank you.
I would like to thank you also at this stage, June. Thanks for being here today with us. I think you have some more time for questions, right?
Yeah, I have enough time. Okay, I think.
Perfect. Yeah, Philippos has another question.
Yeah, hello again. Thank you for your presentation.
Hello.
Yeah. The question is on the same spectrum as the question before, but now, if it's possible, could you compare the packages, the rl.jl and the POMDPs, and if they overlay or if they can be used at the same time?
I think, yeah. To be honest, I haven't used the POMDP a lot, so I cannot answer this question very. I'm not sure I'm the best one to answer these questions. But I have seen that there is kind of overlap. For example, I remember there used to be a DQN related implementations in POMDP organization. But I think we can, as you know, we already have defined a common RL interface together, so that I think our focus will be to complement each other. So we have different focus. Will be especially in the near future. Yeah. So I'm not sure I answered your question directly, since really I do not have much knowledge in POMDP.gl. Yeah.
Okay, yeah, no worries. But do you think we will take that offline? Because I know that there was some questions. Actually, I made some questions on the Julep forum about that, and there was not much activity. And also there is also a question on Discourse. So about this topic. So I could, if you want, I could tag you and start an offline conversation about these two different packages and how can they harmonize in the Julia ecosystem.
Yeah, that would be great. You can drop a message to me on Slack. I'm active. I think I'm active on Slack. Yeah. Yeah, you can just pin me just at June on Slack. Yeah.
Okay, perfect. Thank you very much.
I would have a completely different kind of question. So here's Stefan again. I'm struggling in my mind to understand how the run method for the agent is different from the policy. And I'm not sure whether it's simple enough to directly look into it, but I'm optimistic it could be. And
Yeah,
it would help me understanding how this learning is actually working from the interface.
Okay, yeah. Actually, it's simple. Since agent is also an abstract policy, so here the policy we are executing in the general function. We do not treat agent or other policies, especially. So here the function is a very general one. It only realizes the policy, and it only recognizes abstract policy, as you can see here. But the secret is that when we try to call the policy with the environment, we have we can dispatch it by default. We can have many different dispatched implementations. So for example, if the policy is an agent, then it can inject several customer logic in it. But if it is a vanilla policy, arbitrary policy you defined, then you only implement the policy function, so it will be fallback to the inner one. And I'm not sure if this explains clearly to you. So
that's definitely a step forward. Is there also an easy summary of this agent call? So if the agent policy is called, I guess this is also a generic function then, because yeah, as you say here, the agent has the underlying policy and the trajectory seems to be an abstract interface.
yeah, and here I think, yeah, this actually this part is kind of difficult to explain, and I was planning to improve this part. So some people used to complain that these update methods are everywhere in the package, and it's kind of make people kind of lost in the definition. So I'm working on improving this part. So yeah, I think I will leave it as to answer this question later once I have finished reorganizing this part.
Okay, thank you very much.
Yeah, but the idea is simple. When we are executing the policy for the specific agent related policy, it will inject some logic and forward the environment or the state from the environment to the inner policy. That's all we have done in agent. Yeah. I hope I make myself clear. Okay.
Are there any further questions?
Hi,
Yeah.
Johanny.
Hi, June. Thanks a lot for the presentation.
Yeah.
It's great how far the whole package got in all those years. I really I love it how it works now. One question that I still wonder is, where do you see the main advantages of Julia over Python for developing such a reinforcement learning package? So it still seems that the majority of the RL users and researchers are using Python, even though adoption is growing, which is great. But I wonder, do you see like clear points where Julia is just better than Python in implementing such an RL package?
Okay, so I think there are 2 points I can think of. The best one I think is flexibility, but I think this is too abstract to most users. So more practically, I think I can think of 2 points. The first one is the end-to-end GPU training, especially for example, if you take a look into the Isaac Gym environment, it is an environment very similar to Mujuko, but it runs totally on GPU. And the Isaac Gym provided an interface to expose the state as a PyTorch tensor, so that the code, the several other reinforcement package could use this Isaac Gym environment. But I think in Julia, these things should be much more easier. We can have many different environments written in pure Julia and directly on GPU with the help of code.gl. And then we train our environment directly on GPU. The whole pipeline is written in pure Julia. And I think this is where the Julia shines. And this is one part. And another part is the async part to, I think, for example, in Ray, it already did very well in async programming to use tasks to manage many async environments and train those environments. But those environments are mostly written in Python, and it is kind of slow, I think. So if we can have a whole environment written in pure Julia, that would be much faster, I think. Especially in practice, I find that the speed really matters, because sometimes we really have a very specific deadline, and if you can run more experiments before the deadline, it will usually you can get a much better performance. Yeah, that's 2 points. I think the most important reason to use Julia here. Yeah.
Thanks. Yeah, we need more contributors and users.
Yeah.
Just curious to add to this difference. So from my experience, Stefan speaking again, also having executions which go step by step by step, the Python world is very slow. I'm not sure how it's set up in the Python world, indeed, whether things can be vectorized. But what we've seen today, it looks rather like a simple step-by-step procedure, which we see here in reinforcement learning JL. And that sounds like very suboptimal to realize in Python.
Yeah, and I think in the next step, since the first step is that we move the experience. So I think I will come back to the example. So here in this step, actually currently in current implementation, the experience come into the memory buffer and then come to the policy. This step is step by step and in the sync manner. But when we are running the policy on GPU, we can prefetch the experience from the experience buffer first, so that after the policy has already optimized one step, it can immediately optimize with the next batch. And in previous versions of CUDA.gl, there used to be a bug, so that prevents such kind of async training. But I think that bug has already been fixed in recent versions, and I will do some experiments and enable it in the future. Yeah.
Cool. We have another question from Philippos.
Okay.
Yeah, hi again.
Hi, Philip.
Hi. I was wondering if you could say some stuff about the state of the package regarding multi-agent reinforcement learning.
Oh, okay. Yeah, I didn't cover much about multi-agent reinforcement learning algorithms. Actually, I haven't followed up on multi-agent learning algorithm very recently. So, but in previous versions, I think I have implemented only several CFR related algorithms. But after that, I didn't have time to work on it, and also my personal interest shifted away from it. So the development of multi-agent reinforcement algorithms do not have much algorithm implemented in R.GL yet. And another important reason is that the workflow of multi-agent environment is kind of different from the single agent environment, and the run function couldn't be reused in most degree. So which means if you want to implement an algorithm dedicated for multi-agent environment, actually you have very limited functions can be used in R.GL. The most important, I think the most reusable one is the trajectory related functions. But beyond that, I think we do not have that much to reuse in R.GL. I wished that we can have a GSOC student to work on it, and several students also showed interest in it, and hopefully we will have some people to work on it in the future. Yeah, that's the current status of multi-agent environments in R.GL.
Okay, thank you very much.
Okay.
Scott just commented in the chat that there's still some confusion between the difference when to use AlphaZero and when to use ReinforcementLearning.jl. I would like to add kind of a broader question, whether there are kind of other Julia packages which are similar in some regard to the reinforcement learning package.
So is this a question or is it a comment?
It's more like a question.
Okay.
But it's two questions. Like if you can rephrase it shortly again, what's the difference to AlphaZero? That would be probably very helpful. And also kind of other packages I would be curious in.
To any who Oh, okay. Yeah, I think that confusion is very common, especially, and this reminds me of the early days I learned Julia, because I think reinforcement is a very large domain, and you can see each year there are a lot of papers come out and many different algorithms proposed. So with R.GL, I think I wish this package could be toolbox that people could reuse some useful components to either reproduce some latest algorithm or apply those or write their own new algorithm or reuse RLWL to implement their own algorithm. That's my best wish to about RLWL. And AlphaZero.jl is dedicated to AlphaZero or mu0 related algorithms. I think as a practitioner, I would encourage you to learn both package and try to use the best one that fit in your problem. Then that's my personal suggestion. Yeah. If you find which one is more useful or more powerful in your environment, then just use it and give feedback to the author so that we can all improve the whole ecosystem in Julia. Yeah.
June. I'm also now posting kind of the links of the packages mentioned so far. So we have the reinforcement learning, we have the POM DPS, and AlphaZero has also its own link. And there fits the question whether you can share your resources from today. There have been a couple of links in your slides, and I guess some are curious to have these links also.
Yeah, sure. Will do. I will. Since I haven't uploaded it yet, I think I will add a link to the video link and the YouTube.
Okay, perfect.
So once Stephen uploaded the video recording to YouTube, I will add the link and the YouTube comments.
I guess I have this is Scott here. I guess I have a comment to your answer, June, and also to Stefan's summary, which is, your slide said basically, those of us who have done work in this area in Python would probably echo what you said, which is the ecosystem has many more contributors and there's just much more use in Python. So if the Julia space is smaller, there should be a good reason. Obviously, everybody should work on whatever package they want. I'm just trying to understand if there's enough overlap between AlphaZero and ReinforcementJL. Would it be better for those efforts to be combined so that there would be more contributors on a single ecosystem? It's kind of a political question, and I'm not disparaging anything you've done here. I'm just trying to understand if people are independently creating packages, presumably they're disjoint, and there's a good reason for it. And I don't really understand how they're disjoint or how they're really separate.
Yeah, to me, personally to me, I'm always willing to explore some new algorithm if I find any algorithm already implemented in Julia in other package, I would usually try to cooperate with them and integrate with them. So as you can see, especially recently, I have mainly worked on some other directions. I think the overlap is mainly about some DQN or policy gradient reading algorithm. And also, as I remember, there was a course on the Julia Academy to show how to implement algorithms in reinforcement algorithm in Julia. And but in practice, the most important one is that I do not have that much time to focus on this package, so I can only have limited time to work on the integration part. And it also requires someone who have a good knowledge on both these packages. For example, for me, I do not have much understanding of the POM-DP.jl, although I have a good understanding of AlphaZero.jl, and also I have talked intensively with Jonathan on several possible directions to integrate those packages. But mostly importantly, due to my personal reason that I do not have that much time to work on it. So we suspended cooperation in the last summer. And I hope personally, yeah, I agree with your point that I hope I can have more time in this summer, and I will try to figure out a way to unify our resources so that for users it would make more sense to, or make it more easier for people to choose which tool to use. Yeah.
Just to be clear, I was not being critical of you or the package at all.
I understand that.
That was not the
That's
point of the question.
Yeah, I understand that.
Big thank you again from my side, Jun. Stefan speaking again. We've now reached 1.5 hours, so feels natural for me to say this is it. But if there are some further questions, we can take kind of one more or so. But looks like, okay, there's no urgent question coming up. So then, June, I would like to finish it then. Thank you for being our guest today, our speaker. With this large gap in time zones, I'm very happy everything worked out so smoothly. Thanks for joining, and yeah, looking forward to do more stuff together.
Okay, it's also my pleasure. Bye.